When we talk about probability, there are two main types of probability. There's theoretical probability, and that's the good stuff. Theoretical probability is the true probability. Experimental probability is like the wannabe probability. You can never fully trust experimental probability. But if you do the experiment enough times and you do it properly, you can get a very high accuracy. Never as good as its brother theoretical probability, but you can get a very high accuracy that's quite reliable. However, if you can find the theoretical probability of an event, always do that because it is 100% accurate. It will accurately predict what will actually happen in the future over a long period of time. An example of theoretical probability. When we randomly choose a card out of a regular deck of cards, the 3 of spades will be chosen once out of 52 attempts over the long haul. That's because there are 52 cards, each of them have the same probability of being chosen, and only one of them is the 3 of spades. So one time out of 52, you're going to get the 3 of spades. Even if that's not your experience in life, maybe you did this a bunch of times and it turns out that it didn't happen exactly 1 out of 52 times. Over the long haul is the key. If you were to redo this over and over and over, it will not redo the thing that you experienced. It will redo 1 out of 52. The theoretical probability is always the rate at which things are going to happen over time. Now, the only way we know that experimental probability and theoretical probability are actually very, very close to each other, they'll give you the same results as long as you do enough experiments. Right? So theoretical probability, as soon as you figured it out, you have the actual probability. You know the rate at which this occurrence will happen. Experimental probability, if you start doing the experiment, you're not going to trust the probability. Right? If you keep doing it longer and longer and longer, it'll get closer and closer and closer to that correct probability, that correct theoretical probability. Right? How do we know this? Because we've actually found a theoretical probability of things, and then we've done the experiment, and we found that at first it didn't give us a really good answer. But as you did the experiment more and more and more, and especially with computers where we generated thousands and thousands and millions of experiments of the same thing, we found that that experimental probability did indeed approach the theoretical probability as close as we wanted it to as we did more and more experiments, as we did more and more trials of the experiment. To convince you of this, I actually had everyone in the class do an experiment where I can actually find the theoretical probability. So I knew if our experiment was working. So everyone was to do the experiment 100 times and send in your results. And I put all the results together, and let's take a look at what happened. All right, you were all asked to gather up 10 coins and flip all 10 coins and count the number of coins that landed on tails. So as you can see here, I flipped 5 tails and 5 heads. So I marked down 5 tails. Here I decided to put it on a graph so that we have a better visualization of the probabilities of each one. Each time you flip the coin, that's considered one trial. We can see on my second trial, I flipped 1, 2, 3, 4, 5, 6, 7 tails. And so on the graph, I marked one box on 7 tails. So so far I've done 5 tails and 7 tails. 50% of the time I got 5 tails, and 50% of the time I got 7 tails. Now I'm just going to keep flipping and adding to this graph as I go along, and we're going to look at the percentages as we go through it. Now here you can see, so far I've gotten 4 tails once, 5 tails once, 6 tails once, and 7 tails twice. And so to find the percentages, you simply have to look at the number of trials total. So I've done 5 trials so far. So I flipped the coins 5 times. And of that, 1 out of 5 times, I got 4 tails. And so 1 divided by 5 is equal to 20%. Once I got 5 tails, so again, 1 out of 5 is 20%. Same thing with number 6. And for 7 tails, that happened twice. So 2 out of 5 times, I got 7 tails out of the 10, which means 2 divided by 5, which 40% of the time I'm getting 7. Now keep in mind, we're talking here experimental probability, which basically says when I first start with this experiment, my percentages are not anywhere near the theoretical probability. I cannot rely on these percentages. I can't go to my friend and say, hey, flip 10 coins, and I bet you there's a 20% chance that you're going to get 6 of them, 6 tails and 4 heads. Or there's a 40% chance that you're going to get 7 tails and 3 heads. That's not how it works. But if I keep flipping these guys hundreds and hundreds of times and thousands of times, these percentages will actually end up equaling the theoretical probability eventually, or at least getting very close to them. That's why, despite the fact that theoretical probability is always the best thing to use, experimental probability is valid when you do enough trials. So right now, so far, this is absolutely not a valid experiment because these percentages that I get here are not going to be the same percentages as the theoretical probability. The whole goal of doing an experiment is to try to match the theoretical probability of an event. Now, as I speed through this, I just kind of want you to take a look on the left how not very often does 0 or 1 occur, or even 2 here. That's because it's very rare that you're going to get 0 tails or 1 tail or 2 tails in a flip with 10 flips. Same with 9 or 10. It's very rare that you're going to get all tails or almost all tails. But if you see in the middle, it's accumulating quite a lot in the middle there. And that's because the most likely scenarios are actually the most likely scenario is getting 5. 25% of the time you should get 5. And if we do this enough times, 25% of the time we will get 5 tails and 5 heads. Right? A little less often you should get 4 or 6. As you can see here, 4 we actually are getting more often than 5. Well, that's because we just haven't done enough trials. If we were to do thousands and thousands of trials, the 5 would end up being the largest bar of the bunch. All right, after 76 trials, you can see the percentages here. So 23 out of 76 times, I've got 4 tails out of 10. Only 18 out of 76 times, I got 5 tails out of 10. Now, like I said before, 25% of the time you should get 5. So we're really close on this one. But 4 should have happened less than that. I think it's about 21% of the time that 4 should occur. So somehow we're getting more 4s than what you would normally get. However, it's because we've only done 76 trials. If we were to do thousands and thousands of trials, I guarantee to you that 5 would happen 25%, 4 would happen less, 6 would happen less. And down here you'd get maybe 1 out of I think you'd get 1 out of every 1,024 trials. You would get 1 0 and 1 10. So very few times you're going to get this, and very often you're going to get here. So let's take a look at our actual experiment where we did 899 trials. One person did 99, the rest of the people did 100, and we'll see how our experimental probability matches up with the theoretical probability. I guess first we should take a look at the theoretical probability, and then we'll see how our experiment matches up. All right, we're all familiar with the fact that when you roll a die, you have a 1 in 6 chance of rolling a 3. Or when you pick a card out of a deck when you pick a card out of a deck, you have a 1 in 52 chance of pulling out the king of spades. And that's fine and dandy, but that's because we know there are 6 sides on a die, and one of them is a 3, so it's 1 out of 6. There are 52 cards in a deck. One of them is the king of spades, and so you have a 1 in 52 chance. But what about for flipping 10 coins? So what you have to do is you have to list all the different things that could happen. So the 52 cards, well, there was only 52 possible things that you could pick out. Each card is a different possible outcome. Here the outcomes are you can get heads, all heads on the coin. So coin number 1, 2, 3, 4, they could all be heads. That's one outcome. Another outcome is heads, tails. And then heads, tails, heads. And you could go through all the different unique possible outcomes. And now they all have an equal probability of happening, but look how many there are. There are actually 1,024 different combinations of this. So each one of these guys happening has a 1 out of 1,024 probability, right? But there are many of them. For example, here, this has 2 tails, but also this guy has 2 tails, right? So the number of tails is 2. Well, how many of those combinations will have 2 tails? So what I did is I went through every single one of the 1,024 combinations, and I counted how many of them have 1 tails, how many of them have 2, how many of them have 3, how many of them have 0. And here's what I found. So of the 1,024 different possible combinations, there was only one that had 0 heads and all 10 tails, and that's the only combination was tails, tail, 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 right? So that has a probability of 1 out of 1,024 chance of happening, which is not even 1%, not even 0.1%, but almost 0.1%. So it's like 1 in 1,000 times that's going to happen, right? So when I asked you guys to do 100 trials, it was very unlikely. Only 1 in 10 of you guys should even have had 0 heads even once, right? So if I see that some person's getting 0 heads just as much as they're getting something else, then of course we know that that person wasn't actually doing the experiment properly. Either they weren't flipping the coins properly or they weren't flipping them at all, right? 1 head and 9 tails, well, there are only 10 combinations, so when you want to find the theoretical probability, you just say the number of combinations over the number of total combinations, right? So 10 out of 1,024, that is equal to 0.009, so not even 1%, right? So maybe you guys should have gotten one of those at the most. 2 heads, so you get 2 heads and 8 tails. That will happen 45 times out of 1,024. For a percentage of about 4%. So if you guys did it 100 times, you should have gotten about 4 of those. 3 heads, that should have happened to you about 12 times out of the 100. So that's going to happen more often. 4 heads out of the 10, so 4 heads and 6 tails, that should have happened about 21% of the time, just 20.5%. 5 and 5, that's the most common of all of them. That should happen almost a quarter of the time, just less than a quarter of the time, so 24.6%. And then as you go along, 21%, 12%, right? So how do you find the theoretical probability? You have to actually write out all the different possible things that could happen, and then you count up how many of those would be considered a success for your situation. Right? So let's say I want to know what's the probability of getting exactly 4 heads and 6 tails. Well, it's 210 divided by 1,024. So the probability of it happening is also the percentage of times that should happen. Right? So, and percent literally means out of 100. So out of 100 times, that should happen to you about 25 times. And if it happens, let's say 23 times, and then maybe another time it's going to happen 27 times. But on average, it's going to happen 25 times or 24.6 times out of 100. Let's go to our data. All right, so all of us together we did 899 total trials. Of those 899 total trials, only 2 of them turned out to have 0 heads and 10 tails, like all tails, right? And so that's 2 out of 899, and that is a percentage of about 0%, so 0.2%, right? So not very often. 1 head and 9 tails happened 12 times. 12 out of 899, if you do in your calculator 12 divided by 899, you can get 0.01334816463, and if you move the decimal place over twice, you get the percentage, and that percentage is 1.33, so about 1% of the time. So 1 out of 100 approximately. It's actually 1.3 out of 100. 2 tails, we got 54. So as you can see, it's getting more and more common as we get up to 5. 6 was actually our most popular, but that's just because we only did 900 trials. If we did more, 5 would always be the most popular. Actually, if you combine that with my results from before, the 4 was more popular and the 5 than the 6. And it actually, if you combine it with the results that I did at the beginning of this video, it would actually work out even nicer. All right, so 7 heads, you're going down to 104, 47, 14, and only once did we do 10 out of 10. So here are our results. Let's compare to the actual theoretical probability and see how well we did. All right, don't forget that these results here are the actual percentages that we got when we did our experiment. We actually got 1 out of 189, 100 out of 899 that were exactly 10 tails. We got 14 that were 9 tails, 8 tails, 47. And if you come over to the actual theoretical probability, and that's when I took all 1,024 different possible things that could happen and counted up the numbers, like how many of those possible would be 0 tails, 1 tail, 2 tail, our numbers ended up being pretty similar. Like we got 0% or 0.2% here for getting 0 tails, and the actual theoretical probability is about 0%, 0.1% approximately. We got 1% for 1 tail, and that's the actual probability. We got 6% for 2 tails, and the actual theoretical probability is 4%. We nailed 3 tails right on. That happened 12% of the time, and that's how often it should happen. 19% of the time, we're going to get 4 tails, and it should happen 21% of the time. Very close. 5, we were a bit low. We saw that, but we got 21% of the time. We got it, but it should have been 25% of the time. 22% of the time instead of 21% of the time for 6. As you can see, these 12% of the time right on the money. 5 and 4. Like you could see that we were very, very, very close, right? So if someone were to ask you, hey, what's the probability of getting exactly 6 tails out of 10? Well, you could go 0, 1, 2, 3, 4, 5, 6, 20. You could, if you tell them 22%, well, you're going by the experimental probability. You really should go by the theoretical probability, right? So you'd be wrong to say 22%, but you'd be pretty close because we did enough trials to get not bad. So let's say you just forgot how to do theoretical probability. You could just do the experiment a bunch of times. Just make sure you do it a lot of times, and you could actually get the correct answer anyway. Right? So now you're going to ask yourself, well, if theoretical probability is correct 100% of the time, and experimental probability is correct only if you do it a whole bunch of work, and even then it's still not as good as theoretical probability, what's the point of doing experimental probability at all? And the answer is this. Most of us really aren't gamblers. Most of us aren't only finding out the probability of rolling a die or picking a card out of a deck of cards or taking marbles out of a bag. Most of us care about the probability that it'll rain on Tuesday or the probability that someone will win an election. And the problem with that is there's no cards to pick out. There's no number of cards to count. So we can't find the theoretical probability. So all of the work that's done counting cards that come up spades and counting the number of coins that come up heads and come up tails, all of that is the busy work to figure out that experimental probability, no matter how you slice it, will always come up to be equal to the theoretical probability over a long, long, long period of time. Once we knew that secret, once we knew that, that was the key to finding out the probability of anything, because we could just do the experiment. Right? So when you hear that there's a 90% chance of rain coming up on next Tuesday, that's not because they pick a bunch of cards and they pick a card out of the deck. It's because they went over a bunch of data from years and years and years and years of research, and they found under those conditions, 90% of the time, it rains. And 10% of the time, it doesn't rain. So they can't tell you that it's going to rain, but they could say that there's a 90% probability of rain. Right? And as we gather more and more data, the weather, the way they predict the weather will be more and more accurate. All right, what should you have learned about this today? Number one, if there's some type of event that is happening where you can predict every possible outcome and the probability of those outcomes. Then you can find the theoretical probability. Simply list each outcome with its own individual probability, add up all of the outcomes that would be considered success, and divide that by the total number of outcomes that are possible. If for any reason it's impossible to take the theoretical probability, that's okay. All you have to do is find the experimental probability after many, many, many trials, because that probability will approach the theoretical probability. To find the experimental probability, do the same experiment under the same conditions over and over and over. Record the number of times that there was a success, divide it by the number of times that you tried the experiment. After several trials, that experimental probability that you calculated will approach very closely to the actual theoretical probability, even if you never figured out the theoretical probability. So you can estimate the theoretical probability without doing any of the calculations, just by doing the experimental probability. You should never rely on the experimental probability if there were not enough trials, nor should you rely on the experimental probability if the theoretical probability is available. That's because the results of the theoretical probability are always perfectly accurate. They'll always be the same no matter who does the calculations or how many times. Theoretical probability will always be the same probability. The experimental probability, when done enough times, will always reach that theoretical probability after many, 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 many trials. But this theoretical probability is the correct correct probability. The experimental probability is only used because we know that after doing a lot of work, we can one day get the actual theoretical probability. An example of theoretical probability is the probability of getting a royal flush when you're playing poker. Right? You could easily calculate the number of hands that are actually considered a royal flush divided by the number of possible hands that you can be dealt. An example of experimental probability is the probability of it raining tomorrow. Right? In order to do that, you take the number of days in the past that we've already recorded that have the same conditions as what are about to happen tomorrow, and you take the number of times that it rained out of all those times. So you say the number of times it actually rained divided by the total number of days that have the same conditions, and that's the probability of rain the next day. There is a theoretical probability of it raining tomorrow, I suppose, but it's absolutely impossible to figure out because you'd have to know what every single particle is going to do each time. It just doesn't make any sense to figure it out. But if we gather enough data, eventually our experimental probability, will approach that theoretical probability anyways. So our goal is to collect as much data about the weather as we can, and in the future, our probabilities and our predictions will be very, very close to the actual theoretical probability without ever having to calculate the actual theoretical probability. Your task is to go back to the experiment where you flipped 10 coins at a time, 100 times. Go back and count the number of times that you got exactly 0 tails, the number of times that you got exactly 1 tail, the number of times you got exactly 2 tails, all the way up to 10 tails. And I want you to calculate your experimental probability for getting any one of those. Then I'd like you to go back in this video and find the theoretical probability of each one of those. It's listed somewhere in this video. Then I want you to compare your experimental probabilities to the theoretical probabilities. Afterwards, I want you to discuss it, telling me the difference between theoretical probability and experimental probability, and why they would be different in your case. Then as a conclusion, I want you to tell me which one you would trust. Are you going to trust your experimental probability, or are you going to trust the theoretical probability to predict what would happen if you were to do the experiment again?